Hey there, this is Mr. Mitchell with another science video. Today we're going to talk about superconductors, semiconductors, grounding, and electrical circuits. Go ahead and write down the questions. And we'll get to this page that says superconductors. Let me tell you what a superconductor is. You know, we have understood that whenever you have voltage is the potential energy. The potential energy that goes, for example, through the battery, through the light bulb, and back to the battery. This battery is probably a 1.5 volt battery. But we know that the amps is more of the reality of what is truly going through here. The amps are probably going to be not as high as the volts. Now I know they're in different units, but you're going to lose in almost every single circuit. You're going to lose some energy. It's just kind of the way kinetic and potential energy is in the first place. However, and this wasn't discovered until the 1900s, not that long ago, there are some metals that have zero resistance. And these metals are called superconductors. Imagine what this means. A superconductor, you would be able to just get the ions flowing and let them keep flowing without adding any more power. To use a flashlight example, if you were to turn on the flashlight and just let it shine, right now, at some point, the battery will die down because it will run out of power. But if you could somehow make a flashlight out of these superconductors, then it would just continue to shine and continue to shine and continue to shine, and you would not have to get any power coming from the battery. Because once you get the circuit started, you have zero resistance. That 1.5 volts would continue and continue and continue and continue and continue. Oh, just if this world had all superconductors, you could really have like almost no power bill. Each battery would last you maybe even a lifetime. But as you probably can imagine, that just hasn't been figured out. Maybe your generation can figure it out. But anyway, the superconductors we know of now, they're not that many, and they're actually dependent upon temperature. It has to be really, really cold for most superconductors to actually have zero resistance. For example, mercury. Mercury at room temperature is not a superconductor. But at some point, the colder it gets, it does become a superconductor. Tin is the same way. So it is temperature based. Now, your book is going to say that there are some temperatures that are higher, where some have zero resistance, but from what I've looked up, it seems like most of them are just very, very low temperatures at which these metals truly become superconductors. Now, Ohm's law, you know, this resistance formula is in ohms, and it comes from Ohm's law. I'm pretty sure that Ohm's law was discovered, or Ohm came about before the realization of superconductors. This law is kind of a more reality than it is what superconductors have. Because think about this. If resistance is zero, then you have to have zero on this side. To have zero on this side, voltage has to be zero. And it's just hard to imagine any kind of flashlight or machine or whatever that truly has zero voltage. I mean, you have to have voltage just to get it started. So this formula kind of doesn't seem to work whenever you're talking about these superconductors. On to something else. Let's go to the term grounding. Insulators are used to prevent electricity from leaking, you might say. Now, when I say leaking, that kind of means from jumping to one to the next and from having too much electricity. And it's actually much safer if you have some kind of grounding wire. Now look here, we have this wire that is insulated in green. This is probably some kind of green plastic or green rubber. I have noticed that grounding wire is often green or blue. So it's going to be different from the other colors, the black, the red, that happen to be with these other prongs here. So in grounding, it's important to provide a pathway, and that's what grounding does. Grounding provides a pathway for the current to leave the charged object. Here's what you probably have in this particular thing here. You have the two cords here. The ions are coming through here. Actually, I guess they're coming this way. Once it plugs in, the ions are coming through here and to whatever machinery it has. The electric circuit continues to flow by coming backwards. Pardon me. Coming back through here and into there. Now, you know that you can get too much electricity going through here. So what we happen to have on any three-pronged outlet, this third prong, the one that is shaped differently, is a grounding, I guess you could say, prong. It's the grounding wire. So these two wires right here, the one on this side and the one on this side, are with the positive and negative ions going in and out. But this grounding wire, if we have too much electricity, then it goes through this grounding wire and out to the ground. That's why they call it grounding. And here's kind of a basic look of it. You have energy source, you have power pole, power pole, power pole, and then it goes out to a stake in the ground. The electricity that goes through this goes into the earth, an incredibly large insulator. So the earth can take this electricity much better than, say, an object can. And here's what it looks like. Here's a grounding rod. Chances are good, in fact, chances are almost certain, you have outside your house a grounding rod. Now, it's probably beat down under the ground because you don't really want a whole lot of things going around this grounding rod. Might cut off, accidentally cut this off or something like that. But this is coming from the house, and it is connected to all the three. This wire right here that goes to the third prong, this wire is connected to this. So when you do have extra electricity, it can safely go out here and to the earth, and it spreads out through the earth and is in that huge insulator that you have right there. So that's the purpose behind grounding. And inevitably, three-prong outlets are going to be safer than the two-prong outlets because the two-prong outlets don't have that grounding apparatus right there. Now, you may wonder how you can do something like a truck or a trailer. Here you have a boat trailer. You may not notice that, but this hitch is right here. You have electricity which goes to the lights of this trailer. The lights have to have electricity on the back. So what this is the grounding wire. The electricity that goes from the truck back through the trailer has to have grounding. Now, how are they going to put a stake in the ground? They're not. It actually goes through the trailer to the tires, and then it is at the ground. So as long as it provides a pathway to the ground, that makes it for a good grounding rod. And it's kind of a very smart concept. Ooh, I'm running short on time. Let's go to semiconductors. Semiconductors are here on the periodic table. Now, this looks a lot like these a group that we've had before, these transition metals. Most of them are transition metals, and what semiconductors are is they are naturally insulators. They don't conduct electricity very well unless you add certain substances to them. And then they conduct electricity very well. Then they are conductors. So in their natural state, they're not conductors, but in a state that you can make for them, adding specific atoms, then it becomes a conductor. And probably the most common of this, and probably the best of these, is silicon. Silicon right here, number 14. Many devices actually contain conductors, insulators, and semiconductors. And one of the most common ones is a computer board. Look at this computer board. Wow, look at all the little resistors it has in here. There's a lot of electricity that flows through here, so much you have to have all these resistors just to keep it kind of in control, you might say. Interesting. Now let's talk about circuits. We know a little bit about circuits already, but let's kind of have the official talk about the electric circuit. The electric circuit is the path that the ions flow. It can be from battery through the light bulb, etc. It can be from the power outlet through the light bulb and other appliances, etc. Electrons move from the negative terminal to the positive terminal. Then it adds energy. So as the electrons go through the circuit, the battery then adds energy to it and keeps the circuit flowing. The light bulb can stay on for hours and hours and hours and hours and hours because the circuit is flowing. The battery will put more energy into it and allow the electrons to go through it. Pardon me. This is what's called a closed circuit, and you can see the depiction right here. Now, an open circuit is when the connection is broken, and you do not have any electricity going through here because it is not connected. Once it connects, then you have the circuit again. And that happens sometimes at your house. You may flip a switch and nothing happens. You may have some kind of open circuit that you will want to get closed. Now, a switch looks like this. Now, you have a light switch which serves the same purpose. This switch, if you were to open it up, would make it an open circuit. If you were to put it down, it makes it a closed circuit. Your light switch at home, if you were to flip it up, it makes it a closed circuit because it turns the light on. If you were to flip it down, it makes an open circuit. It turns the lights off. So that's why those light switches work. That's why those light switches work. Now we have and here's what it looks like here. We have this open circuit here, cannot go through, have the closed circuit here, and you have the travel of the ions. Schematic diagram. A schematic diagram depicts the circuit. All electrical devices can have a schematic diagram, and that way it can be read by people all over the world. You don't have the language barrier, you might say. Now, we have certain schematic diagram symbols I'd like for you to know. Just a line is the wire. You can see here open switch, closed switch, resistor. You can see some resistors up here, and it has how much ohms of resistance it has. This here is a battery. Here you can see 6-volt battery. Here you can see 6-volt battery. And what this actually stands for, there's positive on one side and negative on the other. I forget whether it's positive on this side or that side, but that's what's going to have. You have positive on one side and negative on another. And you even have a symbol for the light bulb. Now you can tell some of these can get pretty complicated, as you can see in that example right there. And finally, let's talk about a series. A series circuit has a single path for the current. The current goes here and all around. And if it's broken anywhere, let's say it's broken here, all of the lights shut off. Everything shuts off. A parallel circuit is where you have voltage where each device is the same. The sum of the currents, all devices equal the total currents. So if you have this cut off, then the others do light up. It's kind of like the Christmas tree lights. There are some Christmas tree lights where you cut one off and it's all off. The Christmas tree lights where you cut some off and some stay on. And here's a good example of it right here. Now remember, in a parallel circuit, the voltage is the same throughout here. Okay, hope you've learned. And hey, don't forget to read about this in your science book.